which is Swati Dubey. Swati Dubey is managing this Teach India project for the last couple of years. She learned about Vedic math on her own maybe 6-7 years ago, and then started practicing it in this area in Boston. She lives in Boston area, has a degree in engineering and also has a degree in management. She is a management consultant and also is a corporate trainer. So obviously she has all her skills honed very well, but is going to use it for Vedic math. Vedic math, you might have seen my note this morning. I wrote, I was very skeptical about it. I was more skeptical about the Vedic than math, because I looked at the Vedic and there was really I couldn't find any math in Vedic text, at least not as much as what is being taught today. But I did change my mind in the last 10 years, and now I understand it was a math at that time. So long time ago in India, people were math wizards, and many of you know that all the numbers, 0, decimal point, they were all credit is given to Indian mathematicians. But very, very late in the last year or two, it has come to light that even the calculus that we have today predates Newton. And there is a Kerala School of Mathematics, which still exists, and they were really the original discoverer of calculus. So I think there is something in the soil, and Swati Dubey is from that soil, and I wouldn't take much more time introducing her, but to give her the chance to introduce to you to herself as well as the skills that she is going to demonstrate to us and talk about. Swati Dubey, please help me welcome Swati Dubey.
Hi, good morning. Thank you very much for being here today. And what I'm going to do today is share with you all some of the techniques of Vedic math. I'm a civil engineer, and I have my postgraduate degree in construction management. I've been working with construction industry for the last 10-15 years, and then I moved to academics. I was teaching postgraduate students in India. I worked with many non-profits in India, and I worked with a group which was trying to popularize teaching math in the rural Indian villages. So math is something that I have been always fascinated with. But what happened in we came here in 2005 into the US. So I was doing a distance learning program in Vedic math, and that's where I got all the material from Vedic math. But after I came here, I was working, my daughter was growing, and so I really didn't get a lot of time to study that material. But in 2011, what happened was my company closed, and as any other individual would, I started frantically looking for other jobs. But then one fine day I said, let me just take a step back and think about what are the things I can do more. And that was the time I thought I want to learn Vedic math again. And the best way to learn was to have a goal. So what I did was I contacted the Newton Public School coordinators, and I decided, and we planned to do after-school Vedic math programs for the kids there. So I have been doing this after-school Vedic math programs in Newton Public Schools, and this year in Newton Public Schools too. I have almost, and then this summer I did a small workshop for high school students who had come here for a summer training camp. And that was the time I realized that this technique is fascinating right from second grade to the high school students. So there is something definitely intriguing about this whole Vedic math thing. And now what I'm trying to do is I'm trying to give this tool, this Vedic math tool, to the math educators so that they can bring it into the classroom and make math learning more fun. That's what my goal is. I hope I succeed in that. But today what we're going to do is, I'm just going to share some of the techniques of Vedic math, the history of Vedic math as it is known to most of the people. And as usual, there are controversies, as Dr. Singh did say, that whether Vedic math is really Vedic or is it just math. So there are proponents of it, there are other people who say it just doesn't have any reference in Vedas. But for me, what I personally believe is, whether it came from Vedas or whether it didn't come from Vedas, whether this person, okay, let's just understand what the most popular belief about Vedic math is. The story is that it was discovered by this person who is called Sri Bharti Krishna Tirthaji. And he was studying Vedas and there was this Ganita Sutra. Ganita Sutra means math. Most of the scholars couldn't find any reference to math in those Ganita Sutra. But Bharti Krishna Tirthaji, he studied those whole sutras and he wrote 16 volumes expounding the Vedic system. But somehow, that story is always in flux, as those 16 volumes were lost somehow, whether they were burned, whatever happened. So in his last years, he just wrote one volume of Vedic math, which is still available in anywhere. And according to his research, all math is based on 16 sutras or 16 word formula. So what he has done is he has encompassed whole math into small 16 sutras, and there are 13 Upasutras which are sub-formulae for it. Now, there are people who say that there is no reference of this in Vedas. But if this Bharti Krishna Tirthaji could give us a system which is so amazing, whether he wrote it or whether he got it from Vedas, definitely he needs to have some inspiration from somewhere to come up with this great system. So for us, what we're going to do today is understand what this system is. What is this Vedic math system? And at any point, anybody can just stop and ask me any questions. So what is Vedic math? It is a system or set of strategies to solve a range of mathematical problems. As I said, they are basically based on 16 sutras and 13 Upasutras and are applicable to arithmetic, geometry and algebra. They are applicable, just those 16 sutras and Upasutras can be applied to all branches of arithmetic, geometry and algebra. What we're going to do today is see the application of it to arithmetic, which is the numbers. Basically, how to calculate fast, how to do certain multiplication quicker, faster, easier. So these are the 16 sutras on this side and these are the 13 Upasutras. So these are the formulae and these are the sub-formulae. So they are so simple that they're just one sentence. Like Ekaditen Purvan, that's the formula. How difficult it will be for anyone to remember that. And the translation in English is by one more than the one before. Or if you look at the second one, all from 9 and the last from 10. That's like most important or the first formula that I teach the kids. And you should see them, right? Anytime you say all from, and they just start, all from 9 and the last from 10. So it's just, they are so easy to remember and application is so vast that you would be surprised to see how this small thing, like all from 9 and the last from 10, can be applied to math. So let's go by the first one, which is by one more than the Ekaditen Purvan, which means that by one more than the one before. So what does it mean? This sutra is used to calculate squares of numbers ending in 5. Any number ending in 5, if you want to calculate the square of that number, what you do is by one more than the one before. So take 7, add 1 to it, 7 plus 1 is 8, multiply it by 7, 56, and your last 2 digits are always going to be 25, and that's your answer. So it's that simple. So if you have to do 85 square would be 8 into 9, 72, and the last 2 numbers are always 25. Is it getting clear? No? Can everyone understand this? If it's 105, then 10 into 11. 11025. Yes. Yeah, that's the reason it's 25 at the end. We'll see the application to the other problems too. But this sutra is applicable or useful to calculate squares of numbers ending in 5. Any number. You should be just be able to 425 square, do 42 into 43. $180,625. So take the numbers, multiply by 1 more. That is what it is saying. It's saying that multiply the previous digit by 1 more than itself, and can be used to calculate squares of any numbers ending in 5. Any numbers ending in 5. If it's 185, you multiply 18 times 19. Any questions about this? Sorry? Sorry? No. Yeah, any number. Yeah, sorry. Yeah. Yeah. So it could be any number. If it's 175 square, the number is ending in 5. So you can do 17 times 18, which is 50 plus 56, 6316, and your last digits are always going to be 25. So any number ending in 5, take the first digits, multiply by 1 more than itself, and the last 2 digits are always going to be 25. This can be also applied if the first 2 digits are the same and the sum of last 2 digits is 10. This method can also be applied, or this sutra can also be applied to multiply numbers when the first 2 digits of the number are same and the sum of last 2 digits is 10. What do? The same thing. 6 times 7, 42, and here you multiply 6 times 4, and that's your answer. So if the first digits are the same and the sum of last two digits is 10, you can still apply this sutra saying by one more than itself. Is this making sense? If it's 106 times 104, you take 10 times 11, 110, and 6 times 4 is 24. What would be 92 times 98? 9 times 10 is 90 and 8 times 2 is 16. What would be 102 times 108? 11016. Yep. Yes, again, these are applicable only when the first two digits are same and the sum of last two digits is 10. And that's the reason it works also, that's the reason it comes from, because when you have squares of 5, you have first two digits same and the sum of last two digits is always going to be 10. That's the reason it comes from that whole sutra. When I said the second sutra that we are going to look into is Nikhilam Navatacharam Kashitaha, which is all from 9 and the last from 10. So if I have to subtract any number from, in Vedic math, 10, 100 and any powers of 10 are called as base numbers. And 50, 60, 70 are called as sub-base numbers. That's the basic of Vedic math. So if I have to subtract any number from the base number, all I have to do is apply the rule, all from 9 and the last from 10. So what does it mean is, I subtract all these digits from 9 and only last from 10. So 10 minus 6, 4, 9 minus 5, 4, 9 minus 3, 6. So the kids don't have to do this. All they need to do is, as soon as they have 356, they can write 6, 4, 4. Any digit, sorry. What happens if there is a 0 here? What will be your answer? So what will be here? 0. What will be here?
6.
No. So when there's a 0, you write a 0 and you apply the rule from here. So you will do 10 minus 3, 7, 9 minus 6, 3 and 9 minus 5, 4. If the number that you're subtracting has a 0, you write that 0 and then apply the rule from here. So you will subtract, last is 3. So you will subtract this from 10 and the rest from 9. I can also apply this rule if I have to subtract from 4,000. So what I do is 7, 4, 6 and I just take away and add 3. So this is all from 9 and the last from 10. Same thing happens if I have to do 5,000 minus 1, 5, 3, 2. So what I do is 10 minus 2, 8, 9 minus 6, 3, 9 minus 5, 4, make it 4 and 3. Ten minus, oh sorry, 9 minus 3 is 6. So it's a simple rule of all from 9 and the last from 10. And the application for this is so much in money problems when I teach kids. When they have to learn, I gave them $2. Somebody used $2 and this was 153 cents. What do I do? So the application for this could be in all the money problems and many other things for the kids too. Any questions? Okay, now the same rule, all from 9 and the last from 10, can be applied in multiplication of numbers that are near the base numbers. So we said that our base numbers are 10, 100, 1,000, 10,000. So if the numbers are near the base numbers, this rule can be applied. So first scenario that we are going to do is when the numbers are less than the base numbers. So let's take an example. So what you do is find the base number that is near this number. So what will be the base number here? 100. 100 minus 94 is 6. 100 minus 93 is 7. 7 times 6 is 42. 94 minus 7 is, you subtract this, 87. And that is your answer. You can subtract 93 minus 6 or you can subtract 94 minus 7 and it's going to be the same thing. And you can apply this to any number of digits which are near the base numbers but less than the base numbers. I can go to any number. Yes.
How did you even get that?
So what will be the base number that is near that number? Take away from that, you get 2. Take away from this, you get 5. Multiply 5 times 2, you get 10. Subtract this, you get this. Subtract 998 minus 5. You subtract diagonally or subtract this. You can subtract 9,998 minus 5. Or you can subtract 9,995 minus 2.
So why did you use the 3 zeros just looking at?
Okay, now the trick here is, that's where I was going to come, is that's the reason I took this example is, in the RHS side, the number of digits here should be equal to the number of zeros here 4. So if I would not, I would have said 5 times 2 is 10. I see that these are 2, these are 4, so I would anyway add 2 zeros here. So the trick here is the number of digits in the right hand side column should be equal to the number of zeros in your base number. If they are less, you add zeros before the number. What happens if they are more? So you have 5, you have 20. 20 times 5 is 100. 95 minus this is 75. Now 100 has 2 zeros, right? Here we have 3 digits. So what you do here is you carry over. So 7600 is your answer. So slight modifications in the rule can make it applicable to all scenarios. What happens if it is more? What happens if it is less? Do you want me to repeat this or is this okay? Repeat? Okay. Find the base number which is near to these numbers. 100 minus 93 is 7. 100 minus 97 is 3. 7 times 3 is 21. 93 minus 3 is 90. I check the number of digits here are 2. My number of digits is 100 are 2. So my answer is okay. It's math. What happens if the numbers are more than the base numbers? Here what I'm going to do is do the same thing. Find the base number which is near to these two numbers is 100. Take away 100 from this. So 6, 5. 6 times 5 is 30. And instead of subtracting, I'm going to add here. So the same rule.
What did you add?
Sorry. So when the numbers are less, you subtract. When the numbers are more, you add. And similarly, it can be used to multiply any number of digits. Is this making sense now? Same thing I did. Take away 10,000, 15, take away 10,000, 2. 15 times 2 is 30. I add this to 10017. I see number of digits is 2. I need number of digits 4, so I just add 2 zeros. Yeah.
So you can use it for division too.
Sorry?
You can use it for division too.
Division? No, division is different. We're just doing multiplication right now.
What happens if one of the numbers is less than the base number?
We are doing that too. Vedic math has great alternatives for everything. There are ways, if they are near different base numbers, near sub-base numbers, everything. So today we are just going to cover near base numbers and we'll do, is this clear? Near the base numbers, less than the base numbers and more than the base numbers. Now the third one, what we're going to do is, this is slightly different. One number is more and one number is less. Okay? So what I'm doing is same thing. I find the base number 100. I take away 100 from this. I take away 97 from this. 3 times 3 is 9. Here, I subtract 103 minus 3. Or I can add 97 plus 3 and both the answers are going to be 100. Right?
According to the slide down there, it's showing that you add.
Oh, sorry. No, that's the second one. Let's do the third one. It's a wrong slide there. Add or subtract diagonally. This is the one we're doing. Instead of, okay, I'll take 8 if you want. And then I'm saying that add or subtract diagonally. So what you do is 108 minus 3 or 97 plus 8. Both the answers are going to be 105 here. So you write your answer here 105. Now there is a slight change in our rule here. You multiply by the base number 10500 and then take away 24 from that. So here there is one step more. So once you get this, you multiply by the base number and take away this answer from here. And that's going to be your answer. Similarly, this also can be applied to any number of digits. Once you get the weight, it can be applied to any number of digits. And that's the best part about this is, you'll see small kids asking for like, can I get 5 digits by 5 digits because it's so easy. Like if they have to do like 9, 9, 9, 9, 4 times 9, 9, 9, 9, 2. And they go like 6, 8, 48, 9, 9, 9, 8, 6, 1, 0, 0, 0, 0, 0, 5 zeros. So once they get the method, it's just application of these methods, and once they start doing this 5 times 5, 6-digit multiplication, it just increases their confidence, like they can do all these things. Any questions? No? So basically what we tell in Vedic math is, even if they know their times table is still 5, that's enough. Because if they have to do 6 times 8, they can simply apply this method. 6, 4, 8, 2, 4 times 8, 2, 6 minus 2 is 4. That doesn't mean that they shouldn't know their multiplication tables, but even if they know multiplication tables till 5, that's okay. They can still find this. The third rule that we're going to learn is by one less than the one before. And this is used to multiply any number by 9, 99, 999, any number. Absolutely any numbers. Let's see the first one, which is the one that I'm taking. 567 times 999. What you do is, first, the rule says that by one less than the one before. So you take away 1, 566. That's your left-hand side of the answer. And for the right-hand side, you apply all from 9 and the last from 10 to this number. So 9 minus 5, 4. 9 minus 6, 3. And 10 minus 7, 3. And that's your answer. So for the left-hand side, take away 1. For the right-hand side, apply all from 9 and the last from 10. Give them any number of digits, and this is the best part. That's why I give them 8, 6, 5, 4, 2, 1, 3, 4, 5, 7. Nine minus 8, 1, 9 minus 6, 3, 9 minus 5, 4, 9 minus 4, 5, 10 minus 3, 7. So, yeah, last from 10. All from 9 and the last from 10. All from 9 and the last from 10. So for the left hand side, take away 1, and for the right hand side, apply all from 9 and the last from 10 to that number. Yep. Now here you saw that the number of digits here are 5, number of digits here are 5. What happens if I have to multiply 543 by 99,999? Then what do I do? Simple, same trick that we applied. Make the number of digits the same by adding zeros, and we all know that adding zeros before a number doesn't change the value. Now apply the same rule. Take away 1. 9 minus 0, 9, 9 minus 0, 9, 9 minus 5, 4, 9 minus 4, 5, 10 minus 3, 7. So if the number of digits are less than the 9s, you add zeros to make the number of digits the same. So that's what I'm saying is add zeros before the number to make the number of digits the same, and then apply all from 9 and the last from 10. What happens if these number of digits are more than these? Then what do I do? So we did like 569 times 999 will be 5, 6, 8, 9 minus 5, 4, 9 minus 3, 10 minus 9, 1. What happens if it is 69 times 999, you add a 0 here, 68, 9. Yes? So these were the two that we saw. where the number of digits are same, where the number of digits here is less than here. Now third scenario that we're seeing is number of digits here is more than the number of digits here. So what we do here is split this number such that the number of digits right hand side is equal to the same number of digits here, right? You add 1 to the left hand side. 5 plus 1 equal to 6. I'm just going to put that slide up. Five plus 1 is 6. Take away that 6, 569 from the entire number. 563. And then apply all from 9 and the last from 10 here. And that's your answer. I'm going to repeat this. If the number of digits here are more than the number of digits in nines, you split the numbers such that, so that the number of digits in the RHS side is same as the number of digits in 9. So here the number of digits in 9 are 2. So these are, I split it like this. You add 1 here, 5 plus 1 is 6. Take away that 6 from the entire number and then apply all from 9 and the last from 10 to the right hand side. It's too much, right? It's too much. Do we want to repeat this, or is this okay? Okay?
It doesn't matter if you have a zero inside.
Yeah, it doesn't. It doesn't matter anyway. If it would be 5, 6, 9, 3, 5 times 9, 9, 9, I'll just split from here, even if it's a 0 here.
You don't have to do 5, 6, 9, 9, 9, 9, 0.
Sorry, 5, 6, 9 times 9, 9, 0? No. Then maybe you can do 5, 6 times 99 and then just add a 0. 0 times 9 is 99. Yeah. No, it's the same number. So here, you could, if it is 990, you can apply. Oh, I know how to do this. I just do this and then just add a 0. So when they say, okay, learn the tricks, how to do like 5, 6, 8, 3, 4 times 99, 9. Now you know how easy it is, right? You don't have to worry about, oh my God, how do they people do this? We can just write it very quickly. 5, 6, 8, 3, 3, 4, 3, 1, 6, 6.
How the human calculator did all the calculations?
No idea, maybe. But this is definitely faster than a calculator. Because even to put these numbers in calculator is going to take time. Does anybody want to come and try? Come. Yeah, you would. I think I'll help you. Take away 1. Take away 1, yeah, 32, yeah. And then apply all from 9 to the last one, 10. Yep. Got it. There are many such tricks, or many such, I wouldn't say tricks, they're techniques to multiply the numbers when there are certain scenarios. We have the scenarios where they are near the sub-base number, where they have near different base numbers. But now what I'm going to do is, I'm video. What's the time? Oh, okay. Okay, I'm just going to do quickly this. This is the one which is used to find square. It's an application of something what we have learned. This sutra can be applied to calculate the squares of numbers near the base numbers. What do you do? 96 square. If I have to do 100 minus 96 is 4. So find the deficiency. That's what it says. Whatever the deficiency, lessen by that amount. So take away that 96 minus 4, 92, and square the deficiency. And that is your answer. I'll repeat again. What it means is, first find how far or what's the difference, subtract it from the nearest base number. Whatever is your answer, take away that number from this number, 92, and then for the answer, square the deficiency, and that's going to be your answer. $98 square would be 96? 64. No, 9604. Yep. 100 minus 98 is equal to 2. 98 minus 2 is equal to 96. Square the number. 2 square is 4. Our rule is that the number of digits should be the same, so you will add a 0, so 9604. Yep. What happens if the number is more? 103 square? Same thing. 103 minus 100 is 3. Here, you add that deficiency or whatever the difference is. 106, 3 square is 0, 9. So you can find squares of numbers near the base numbers by any, whatever it is. Will be how much? Nine, 2, 0, 0, 1, 6, right? And then square of 4 is 16. Okay, and the last but not least, is to multiply any number by any number. What they have is vertically and crosswise. To multiply any number by any number. Right now we just saw some techniques to do multiplication when in special cases or in special scenario. What happens if I have to multiply any number by any number? 62 times 96. The rule is called as vertically and crosswise. So what you do is, first do 9 times 6, 54. 6 times 6 is 36. 9 times 2 is 18. And 6 times 2 is 12. So we have 54, 54, 12. 2, 5, 9, 5. Whenever there are 2 digits, you carry over. Sorry, I'm just rushing this just to tell you that Vedic math does have a way to multiply any number by any number, and this can be used to multiply any number of digits. Any number in one line. If we had time, I would have done this, but we're running really. And so all I'm saying is, so you see what is Vedic math is, you can do a simple 91 times 99 by 4 ways that we learned today. The first one was by 1 more than the one before, where you multiply by 1 more, add 9 times 10. The second one was when you have to multiply by 99, take away 1 and all from 9 and the last from 10. And the top one is the cross one, and this is the vertically uncross one. So the kids or you have more than one way to solve the problem. It's not that if any multiplication is given, you are just doing the same way. Whatever you remember, whatever is intuitive, and that's the reason what they call as Vedic math is it is flexible, intuitive, fast, better accuracy, easy, and people can really do it in their life with more practice. Okay, questions?
I'm sure there are a lot of questions, but I think she has about 5 minutes because she has very, very grateful to her that she came today because she had another class in Boston area to go to. And so, but there are some questions, maybe a couple of them she can answer.
Yep. Sure. Polly, I'll give it to you and you can just either email it to you, that's okay? Yeah. You can, the handouts? Oh, sure. Yeah, sure. Yeah. Yep.
Can you give her the microphone?
Okay, quickly.
What was the question?
He wanted to know how to do the divisions.
Oh, okay.
Okay. I'm just going to show how to do division by 9. If 3, 4, 1, 2 divided by 9, you just draw this one first. Split it so that this is the remainder part. 3 plus 4, 7, 7 plus 1, 8, 8 plus 2, 10. Right? So you got this. This is your remainder, 10. But remainder cannot be 10 when you're divided by 9. Because 10 divided by 9 will give us 1 and 1 remainder. That 1 is going to come here. So your quotient is 379 and your remainder is 1. So you're just doing 3, 4 plus 3, 7, 7 plus 1, 8, 8 plus 2, 10. So the kids who don't even have the concept of what is division or how to do it, they really get it, like, even if they're starting, because there's no division here. They don't even need to know the 9 times table till they go here.
But doesn't it conflict pedagogically the way we teach math is different? And you
It
teach
is.
it Vedic way to fix it.
But the basic of Vedic math is you really need to know the 4 operations. And I'm working on how to teach, like how to teach multiplication tables too. There is this method, 4 times 3, to a preschooler. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A preschooler can really write this multiplication tables, and that's they do, second grader, third grader. I'll take, and 9 times table, does anybody know 9 times table? So what you do is do this. 9 times 1 is 9, so count the fingers on the left hand side. 9 times 2 is 18, 27, 36, 45, 54, 63, 72, 81, 90.
And who is to say which pedagogy is better than the other way? We just know the other one, so that's why we think this is unusual. But maybe this is more usual.
This is, yeah, and this is, you can do all the multiplication like 9 times 9 with the fingers.
This is how the Umum access with the math.
They are different. Yes, sorry.
My question is, how close are the numbers supposed to be with the base number?
If you can multiply the two sides, the point of this method is to make it easy. So if it comes to like, if you have to do something like 63 times 64 here, and you're okay with it, do it. The point is, if you cannot, then use another method. So if you have some deficiency which will give you 63 and 64, and if you know how to multiply these two numbers, then that's fine. Something that will make your life easy.
Another question? I have a question. I wonder, this is related to what Siva just asked question. I wonder if there is going to be difference in the brain. People do different kind of math. This is known, language affects the brain. Math is also a kind of language. It is more natural language to me than this one we speak. I wonder if there is any study done whereby people...
There is, I tried to find any factual information, but people do say that, yes, it is showing better results, better understanding, and it's definitely more fun, and definitely my experience with the kids is they start liking math and they develop confidence in math. But they are very clear when they say that I like this math, I still don't like math in the school. So they are very clear in that. Because the first time they come to the class, they are like, I don't want to be here, I don't know why I'm here, my mom put me here. And we actually have I hate math and I like math. And then at the end of the 10 sessions, I asked, do you want to move here? They're like, yeah, I like this math, but I still hate that math in the school. So it tells you that was the reason I started teaching, because I wanted to see how it is affecting, whether it's really relevant today too. And it is. Definitely it is.
I may have a comment.
Yeah.
This approach is more great than that.
And did everybody hear that? You're saying that this approach is more right brain?
Or whole brain.
Whole brain.
Than that brain.
Okay. Well, that's...
Yeah, because it's flexible, intuitive, and everything, yeah.
Well, it will be very interesting if we found a way to study this when people do this kind of math as to what happens in their brain imaging or something like that. That would be really fantastic. So we really would like to thank you very much for taking the time to come, and I have a very small token of gift for you from Center for Vedic Studies.